shooting.
Hello, fellow physics friends. Today, we're going to learn how to lose or gain weight fast and with no effort. A theory. So, when a person is on a scale, there are two forces acting on them. Gravity, which is their weight, times the gravitational standard, 9.8, and the normal force, pushing back up onto them. Now, if this was to be put into an elevator, when it's at rest, it would stay the same. But if the elevator were to accelerate upwards, due to Newton's first law, an object at rest stays at rest until another force is acting upon it, the person would want to stay where it is as the elevator moved upwards, creating a greater force downwards, which would create a greater force on the scale, making you weigh more. For example, a 65 kilogram woman is standing on a scale in an elevator. At rest, her weight would be 65 kilograms times 9.8 meters per second squared, which is equal to 650 newtons. Now, once the elevator started to accelerate upwards, say at a speed of 1.96 meters per second square, it changes the equations, because if it's not at rest or at a constant speeds, the sum of the forces is not equal to 0. So that means tension minus the weight is equal to mass times acceleration. Backtrack. Editing.
Got all that, Peanut?
So that means that the normal force minus her weight is equal to mass times acceleration. Subbing in what we know, we find that normal force minus 65 times 9.8 meters per second is equal to 65 kilograms times 1.96 meters per second squared. Then you have normal force minus 650 newtons is equal to 127.4 newtons. Add 650 newtons to both sides, and you get the normal force is equal to 777.4 newtons. Divide by 9.8 meters per second squared to get back into kilograms, which is 79.33 kilograms. Do you want to take a bathroom break?
Sure. And Peanut agrees. Yeah, Peanut! Woo!
I don't think. Now onto the important part, how to lose weight. We'll take the same scenario with the 65 kilogram person. And let's say they're doing, this time, a downward acceleration of 2 meters per second squared. We use the same equation that the sum of the forces equals mass times acceleration. But this time, since the elevator is traveling downwards, we make the weight force, or mg, the positive force. So we do mg minus the normal force equals ma. We substitute in what we know. So 65 kilograms times 9.8 meters per second squared minus Fm equals 65 kilograms times 2 meters per second squared. And then we get 650 newtons minus Fn equals 130 newtons. We subtract 650 newtons from both sides. And then we get negative Fn equals negative 520 newtons. We multiply both sides by negative 1 to get Fn equals 520 newtons. And then we divide by 9.8 meters per second squared to get it back into kilograms, which is 52 kilograms. So this 65 kilogram woman will now appear to weigh 52 kilograms on the scale. Overall, if you're on an elevator, if the elevator is at rest, the scale will read the same weight that you weigh. But if you are going in an upwards acceleration, at the moment of acceleration when the elevator goes, you will weigh more. And at the moment of downward acceleration, you will weigh less. Also, if the elevator is in constant motion, you will just weigh the same mg because the sum of the forces will still equal 0. Now let's go see if it actually works. Hello, we're at the Towson Town Center parking garage elevators to test how your weight changes on the elevator. So we are standing regularly on floor 6. 113. Zoom in. Okay. Now we gotta catch the elevator.
Going down.
Okay. Should I wait till it goes?
Go. Get on, Brooke. It's moving.
Now it's at 46. No, it's going up. 50? It was at 46 for a brief moment.
Okay. And now it's at 50.
It's at 46.
It goes to 46.
And when we stop, it goes back up to 50 something.
50.
To 50. Alright, now we gotta go up again. Now they've got it figured out.
Okay. So going down, everybody remember, 46 to 50.
Up. It's at 50.
It's not gonna change as you're gonna have to do it like
It went. It was at 50.
at 1.
Go back up.
Up doesn't change.
It's staying at 50.
It's just staying at 50. It was going down. It
I
changed.
feel like the scale just sets. You'd have to like.
That's what I was thinking.
As the elevators go up, then step
If
on.
I would have had the big one, it's an actual
Yeah,
weight.
that doesn't. All right, last time. Now get off. We're gonna go down to what number? 2.
Going down.
48.
It goes down. It goes to 46 going down. That's it. So let's go use that data. Done.
All right.
46 going down. It doesn't change. Brooke? Yep.
Going up.
It's at 51.
No, let's see what number it is when it stops. I think we've out welcomed. Oh. What number? Going down. We'll try one more time. See.
Should I stop the video?
Yeah.
Oh, it's going, it's going.
But we're going down again, Brooke. We're not going up.
Where are we about to go up? Okay. Now, from 6 to 1. I lost 2 pounds.
Well, that didn't work.
Okay.
Oh.
We'll up at 6.
Going up.
Maybe.
We're here, and we are at the Towson Town Center
going up.
parking garage elevator to weigh myself.
Come on.
Y'all going down?
Up.
Oh, up, no.
No, it's going down.
It
No,
said
no,
up.
wait, we do want to go up. We're going to 4.
Okay, you're going up.
Is that a scale?
Yes, it's a science experiment.
Oh, you trying to see how your weight changes when it goes up and down?
Yes.
Does it really work?
Yes.
Well, we're going to find out.
Yeah.
Wait, what level are we on?
Well, we're gonna get off at 4 here in a minute.
I feel like we're going down.
I pushed 6.
I'm still filming.
No, we're at 6. We're at 6.
Oh,
we're getting
my
off at
God, how we
6.
go 4? Oh, y'all getting on? Okay.
All right, we're getting off.
We're going to 4.
It didn't say up top.
Stop.
In conclusion, we found that it's a lot harder than it looks / what the math says to make you gain and lose weight. And that is the physics truth.
And let's give credit to Mother for driving you all the way down to Towson Town Center. They love me. They love me.
It goes better on the side view.
Yeah.
I don't know why I'm filming this now still.